Good morning, everybody, and welcome to Cleveland's National Chemistry Week for 2012. Before we get started, one of the things I'd like to make everybody aware of is please don't touch anything in front of you until you're instructed to do so. Please don't put anything in your mouth, okay? And just act like grown-up chemists and just be very, very careful when you handle everything. The subject for National Chemistry Week this year is something called nanotechnology. Does anyone know what nanotechnology is all about? What is nanotechnology all about?
It's like very small things.
How small is small?
Like microscopic.
Like microscopic, like very, very small.
And then like nanobots, nanoparticles, nanocoating, stuff like that.
He's really on top of things, isn't he? Okay, well, nano is all about, like you said, all about very, very, very small things. And I think before we go too much further, let's have a fun little video to watch to really introduce everybody to what nano is. You've seen the stars of the show. Let me introduce a couple of people around here. First of all, I'm Bob Fowler. I'm with the Cleveland section of the American Chemical Society. And my colleague, Lois Kuhns, back in the back. Lois, say hello, Lois.
Hi.
Lois is busy handing out goggles. We'd like to make sure that we thank John Carroll University for having us out and for sharing their facilities with us. And also for filming this program today. Hopefully it's all going to end up on YouTube. And we thank Austin Larkin for coming out and actually doing the filming for us. Okay, so you've seen a little bit about what nano is, but why is nano important? It turns out that nano is a very, very interesting new branch of science. It's only been around for about 50, maybe 60 years at the most. Why is nano so important? Why is studying small things all that important? Anybody have any ideas? You had some ideas a minute ago. Any ideas about why nano could be so important?
No.
Okay, he doesn't. Well, I have a couple of things. First of all, people, doctors in medical research facilities are finding that you can detect certain kinds of cancer and actually cure some kinds of cancers using nanotechnology. Did you notice the nanotubes during the program? Those are actually being used to increase the life and the power of batteries. And DNA, we're actually using nanotechnology to splice, that is to cut into DNA so that we can better understand who we are and where we come from. Well, I just wonder if maybe some of our young friends have seen a program called the Magic School Bus. You guys have seen the Magic School Bus. Who's the teacher in the Magic School Bus?
Miss Frizzle.
Mrs. Frizzle.
I forget. I watched these in kindergarten.
Did you ever see an episode in which the entire crew was shrunk down to a size so small that they could actually go into blood vessels and see blood vessels?
Yeah, I've seen that.
Remember that one? What happened in that one? Did they go inside a human body? Pretty cool, isn't it?
Yeah, it was funny.
That is pretty small. Blood vessels are very, 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 very tiny. And if you can imagine actually shrinking down to go into one, that would be a fantastic thing to do, right? Well, with nanotechnology, we can't shrink people, but we might be able to come up with some nano machines that could go inside bodies and look inside things. Now, with Mrs. Frizzle, she has a pet in the program. Remember the pet's name? What's the pet's name?
Lizzie.
Lizzie. Lizzie the lizard, right?
Yeah.
Well, we don't have any Lizzie the lizards with us today, but we are going to go on an imaginary trip, much like Mrs. Frizzle did. Don't take the goggles off, please. You got to have the goggles on all the time, okay? We're going to take an imaginary trip, and we're going to have two imaginary people guide us on our imaginary trip. These people are going to be professors. Who?
get their names.
Professors Millie and Professors Avogadro,
I
right?
know what they look like.
You know what do they look like?
They look like cartoon characters.
They look like cartoon characters. Well, what's going to happen is Millie and Avogadro are going to guide us through the program today. And at the end of the program, Millie and Avogadro would like to ask you guys a couple of things. And if you look on your place in front of you, there's a little what we call feedback form. And on here, it gives you the opportunity to tell us which experiment you liked the most and which experiment do you think helped you learn the most about nanotechnology. Okay, so we're going to ask you guys to fill that out. So as you go, remember the experiments that you liked the most, and we'll ask you to fill that form out at the end. Now, if you don't fill it out at the end, if you don't have a chance, you can always go to our website, and please take this little document home with you. It talks about nanotechnology. It has all kinds of fun things for you to do on it, and there's a link on the back right up at the top to our website. And Austin tells me we can actually put the link on the videotape so everybody can see that and go to it whenever you want to. If you go to the website, you'll be able to find a survey form, an electronic survey form, much like this one. So if you don't get a chance to fill this one out, please go to the website right here on the top and go ahead and fill out the survey that way if you would, okay? Now, when things get very, 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 very small, things called, when matter gets very, very small, things called physical properties begin to change. Anybody have any idea what a physical property is? What do you think?
It's like something that explains the object.
Yeah. It's how things look. It's how they feel. It's how heavy they are. So it's all kinds of things about the material. Well, it turns out that when things get very, 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 very small, some of the normal physical properties can change drastically. Like, for example, you've never seen the foot of a gecko, but have you ever seen a gecko walk upside down on glass? That's because, or the gecko is able to do that because of some very, very tiny nano-sized hairs that are on the bottom of its foot. It allows it to actually get suction and walk on the bottom of a piece of glass. Other things happen when materials get very, 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 very small. Sometimes if something wouldn't dissolve in water as a big size, when it gets down to a small size, it will. Some things don't burn when they're in a big size. When they get down to a small size, they will. And one of the most interesting things that happens when materials get smaller and smaller and smaller is that the color of the material can change. We're going to see examples of several of these things today as we go through the experiments. Color is a particularly interesting one. We're going to see something today that can change color in 3 different ways. It's going to be actually gold, and we're going to see gold in 3 different colors depending upon the size of the particles. Now what we're talking about with the gold is everybody has seen a regular size of gold, regular gold, maybe rings and jewelry and so forth. You know what color gold is. But chemists can actually make gold in very, very, very tiny nano-sized particles. And when particles get that small, that's when they change, when the physical properties change for all kinds of highfalutin chemical reasons. But colors can change and other physical properties can change. So let's take a look at some examples of that. But first of all, let's see if we can figure out about how big a nanometer is. What kinds of things can you think of that are very, very small? You guys are, what's the smallest thing you can think of that you can see with your eyes? What do you think? How about a grain of sand or a piece of salt? Okay, salt out of the salt shaker. That's pretty small, isn't it? Now, Imagine in your mind that you could take, say, a grain of sand, and you've got a little magic knife, and with that magic knife, you can cut that grain of sand in half. If you cut that grain of sand in half, and then cut it again, and again, and again, and again, can you imagine that? Cutting that grain of sand in half over and over and over again. If you cut it in half 13 or 14 times, each time you cut the half in half again, you're down something to the size of a nanometer. A nanometer is 1/1,000,000th of the size of a grain of sand. 1/1,000,000th of the size. Now, we can't really look at nanoparticles, really tiny little particles today, because when scientists look at these materials, they have to use special, powerful microscopes called electron microscopes, typically. We don't have one in the room today, so what we're going to do is we're going to pretend that we can get down to nano size by starting with a simple piece of paper. If you would, take the piece of paper, the piece of plain paper that you have at your place, fold it in half. We're going to eventually here tear it in half, just like we cut that imaginary grain of sand in half. So, fold it, and then fold it the other way so that it will tear easily on the fold. When you've got it folded a couple of times and it will tear easily, go ahead and tear it in half, carefully. Keep the first half and put it aside at your place. We're going to use that later for other things. But take the other half of the paper and fold it again. Fold it, and then fold it the other way so that it will, you can tear it again. And keep doing this. And let's see, as we tear these things, who can get the smallest piece of paper. Keep tearing and tearing and tearing. This is like cutting that piece of sand over and over and over again, cutting it in half over and over and over again. Now, if you could imagine that the piece of paper, just imagine in your mind, the piece of paper was a grain of sand. Now, surely it's much bigger than a grain of sand, but imagine that it's the same size as a grain of sand in your mind, and what you're doing is you're tearing it apart. And you're cutting it, and you're cutting it, and you're cutting it over and over and over again. Okay? I'm down to something that, whoops, that looks about like this so far. Okay? We're going to keep tearing and cutting, and folding and tearing and folding until we get down to a very, very tiny piece. And this is like cutting that grain of sand in half again and again and again and again, to try to get down, in our mind, to a nanometer size. Okay? And we're going to tear it again and again and again. Once it gets small enough, it's easier and easier to tear. Usually just a single fold, and it'll tear without too much trouble. Lois, if you could start putting around some of the warm water, I think it might be a good thing to do at this point. Okay, I'm down to this size. Okay, how you guys doing? We want to get down to a very, very, very tiny size. You can see the point, though, that what we're doing is we're getting smaller and smaller and smaller. Now, imagine that when you're done, maybe we'll have something that is about the size of a real piece of sand. Probably a little bit bigger, but somewhere down there. And when it's all said and done, now that we've torn this thing, I don't know, I've torn mine about 10 times. Yeah, I'm gonna take those out. We're down to something that looks about like that, maybe a quarter of an inch. And I'm gonna see if I can tear it even more down to a very, very, very tiny size. Tiniest size I can get. I think my fingers are too big to carry it, to tear it too much further.
Its properties are changing.
Its properties are changing indeed, so are my fingers' properties. Okay, at each table, someplace, there is a 10 ml vial that says just W on it. No, not that one. There is a 10 ml vial, there it is, a 10 ml vial. If the first person at the table could take the 10 ml vial that has water in it, it has W on it, take that waxy tape off, that's called parafilm, take that off and open it up and first person, put your piece of paper into the water. And then pass it down. That's pretty small, that's good. Pass it down, we're gonna shake it up in just a minute. Whoops, you just dropped it. Put your piece of paper into the water.
That's my nanometer.
You're not done yet? Okay, well you will be.
Sure. Yes.
Yeah, it's a vial, a 10 ml vial marked with W.
Rub it against the ruler.
Take the parafilm off, and everybody put their little piece of paper in there. Okay, now after you've done that, and you've got the tiniest piece of paper that you can, you'd have to tear it in half maybe 13, 14, 15 more times to get down as small as a nanometer. Can you imagine in your mind how small that is? 1/1,000,000th the size of what you have there as a piece of paper. Okay, does everybody have the piece of paper in the vial? When the last person has the paper in the vial, please put the cap back on and shake it. Put the cap on really tight and shake the vial. We want the water, we want the paper to be in the water, all the pieces of paper in the water.
All the pieces of paper in the water?
No, the two little pieces of paper from each individual. Okay? Each person's piece of paper needs to be in the water at this point. Now, if we shake it just a little bit, what's happening to the water? Is it turning a little bit cloudy? Okay? The paper is actually beginning to dissolve a little bit in the water. Okay? Now, what we're going to do is we're going to set that aside just for a minute, and we're going to come back to that a little bit later. We'll be using it a little bit later. Okay? Now, the next thing we'd like to do is I'd like for everybody to do an exercise for me. Everybody please stand up. Okay? And put your chairs in, get behind your chairs, so you're free to move out just a little bit. Can you stand up? No? Can't stand up? Okay, that's all right.
My leg.
Okay, everybody, would you put your arms out and link arms with the person next to you? Okay? So that's fun, okay? Yeah, find somebody else to link arms with. Okay, when I say heat, this is the position you go into. Okay? When I say cool, spread out and just hold hands. Cool. When I say deform, everybody lean over a little bit. Heat. Cool. Okay, you guys have got the idea. And the last one is deform. Okay. Okay, sit back down. And the second experiment we're going to do is with something called a memory wire. And just a regular piece of wire, it turns out. At the nano scale, at the very, very tiny scale, we're on an atomic level. And things are going to happen with this memory wire actually at the atomic level. Have you guys ever thought about the fact that water can exist in several different forms? It can be ice, it can be liquid, or it can be steam, right? Put water in a pan on the stove and heat it up, you get steam. Okay, I just said the magic word. Heat the water on the stove, and it changes from one form, we call that a phase, from one form to another. Well, the memory wire that we're going to check in just a minute is also going to change from one phase to another. These are called, chemists call these solid phases, but they're a change nonetheless, just like water going from liquid to steam. So at your places, there are 4 little pieces of wire, very, very thin pieces of wire. Everyone please get a piece of wire. There's also a paper clip. If you would take the paper clip and open it up so that it's more or less a straight piece of wire. Yeah, just unbend it so that it becomes a straight piece of wire. Sit the paper clip down when you're finished. Now you also have a pencil, or get a pencil. There's pencils in the cup. Everyone get a pencil. You pass them down. Now, starting with the blunt end of the pencil, let's hold the memory wire, the little thin piece of wire, against the blunt end of the pencil and wrap it around and make a little coil out of that memory wire. You know what I just said to the memory wire? I just said, deform. Remember what happened when you deformed? You all leaned. That's what's happening here at what we call the atomic level. You can't see it happening, but the molecules or the atoms are all leaning in a different direction. Okay, now take your piece of memory wire, and at each table there's a cup with some warm water in it marked HW. Take your little coil of wire and watch what's going to happen now. Take it and drop it in the hot water. And tell me what happens.
Go straight.
Oh my.
That's incredible.
Oh my goodness, it went straight. How about that?
That is totally weird.
What's weird about it? That's nanotechnology. That's good stuff, right? You know what I just said to that wire? I just said heat to the wire. And it went like this. It went back to its original shape that it had when we started. Let's see what happens if we take the paper clip and put the paper clip in the water.
It stays like.
Did it go back to its original shape, its curlicue shape? No, only one of them did. The memory wire is the only one that went back. Now, you guys can take the memory wire and the paper clip home with you, and you can try this over and over again. Now, watch out because the water might be a little bit hot. Okay? So we said heat, and the memory wire, the atoms of the memory wire aligned all back up again really tightly, and that's what caused the memory wire to go back to its original shape. All right? The next thing we want to do, let me get my list of tricks here. The next thing we want to do is with the little tube in the front of you on the table that has the black, gunky looking liquid in it, and there's a letter F on that. There's also a little magnet. The magnet might be with the gunky stuff in the tube. This little tube right here. Or it might be separate from it. What I'd like for you to do is take the magnet and hold it up to the little black gunky liquid in the tube. Don't open the tube. Hold the tube horizontally. Hold the tube horizontally and put the magnet up against the liquid. And tell me what's happening with the fluid. What do you see? Yes, what do you see?
It's coming together because if I take it off, it goes like that.
It's coming together. Do you notice anything different about it? Look very closely. What do you see?
It seems to be magnetic.
That seems to be magnetic.
There's
Well,
little
I think you're
thorny
right.
things on it.
Hmm?
It looks like there's little thorny things on
Little thorny things on it. Does everybody see the little thorny things on it? What we have here is the fluid called a ferrofluid. It's made of nano-sized particles of iron. Iron is magnetic, right? But because the particles are so small, and because they're in an oil with a little surfactant in it, they actually are suspended in the liquid. So if you take the magnet away, try taking the magnet away and shaking the vial a little bit, you'll see it go right back to a normal fluid. This is a really interesting fluid. It's used as a sealant for some special bearings. It was developed by NASA, actually, back in the 1960s. So after you've shaken it up, if you take the vial and you hold it horizontal again, and you apply the magnet to it again, you'll see that you get those little spiky things forming in there, because that's a response to the magnetic field applied from the magnet. And if you look carefully, you'll also see some little spirally lines around the side of the vial once the magnet has done its thing and attracted the fluid to it. Those little spirally lines are the actual field, the magnetic field induced by the magnet. Does everybody see that? Everybody see the little spiky things? Somebody's still fooling with the memory wire. It still works, doesn't it? You can take that memory wire and coil it and put it in the hot water and coil it and
it.
put it in the
What
hot
happens if
water.
you put it in cold water?
Nothing. Because remember what we said? I said heat. You guys all got together. And when you all get together, that's what that looks like. Okay, that's what's causing that thing to go back to its regular shape, to its original shape. Okay? Alrighty. That's called a ferrofluid. It's lots of fun to play with. And by the way, if you go to the internet and Google some of this stuff, Google ferrofluid, you'll find all kinds of neat YouTube videos on ferrofluids and how they're used and what they're all about. Okay? Now then, let's go to the next little thing we want to do. At everybody's table, there's 4 tubes, 4 nanotubes, 4 10 ml vials, marked N. If everybody would get one, please. There's also a single tube marked G. You kind of have to look a little bit to see the G. What I'd like for you to do, first of all, is take the little 10 ml vial marked G, and the person who has it, take the other half of the piece of paper that we set aside, at least some of us did. Okay. The other half of the piece of paper, and hold that vial against the piece of paper. What color is it? What color is the fluid in the vial? It's light, but the color is definitely there. What color is it?
It's like
What color is it, guys?
It's like kind of like a yellowy green.
Kind of like a yellowy. Okay. Pass that down, and everybody have a look at that against our piece of paper, and make sure that you can tell it really is in fact yellow. Does it look yellow to everybody?
Yeah.
You know what that is? That is what we call a salt of gold. So that's gold in its normal physical size, okay? Now what do you think would happen if we somehow made gold, little solid gold particles that were of a nanometer size? What color do you think they would be? Anybody? Yellow? You would think that if you take something and just shrink its size, that the color wouldn't change. You would normally think that, right? But on the nanoscale, funny things happen. Let's take the tube that has the pink liquid in it. And look at that. Everybody has one of those for their own. Look at that against the paper. Does it look absolutely crystal clear, or is it a little tiny bit cloudy?
It is cloudy.
A little bit cloudy. Now compare that yellow, the tube with the yellow liquid in it again. What is the yellow liquid? Is that clear or is that cloudy? Hello, anybody?
Clear.
Clear, thank you. Okay, so we have the one with the pink fluid in it that's cloudy just a little bit, and one with the yellow fluid that's fairly clear, right? What we have there is an example of what chemists call, in the case of the yellow one, a solution. And the pink one is called a suspension. And it turns out that a suspension is actually tiny solid particles suspended in a liquid. In this case, the tiny particles are somewhere around 3 to 15 nanometers across in diameter, and they are gold. So that red fluid that you're looking at is actually gold. Okay? Okay, Lois, how do you turn this silly thing on?
Turn it to the top.
There we go. Okay, what we're going to do is we're going to try to see that a little bit different way. I'm going to come around to each of your tables, and I've got a light. What chemists do to determine whether or not we're dealing with a suspension or a solution, at least sometimes, is shine a light through it. If we have a suspension of solid, little solid particles, and that's what the pink ones are, those are actually suspensions of little gold particles. When we shine a light through it, you'll be able to see the light beam in the solution. For the clear one, which one is the clear one?
That's
The G. Where's the one with the G on it? Here it is. If we shine the light through that, you can't see the light in the liquid very well. This works best with a laser, I think. Lois and I have had our debates about this. She's shaking her head no. But this is...
Not with kids, not with kids.
I know. We can't use it with the young audience that we have. But this is called something that the chemists call a Tyndall effect. So let me borrow your tube here.
sure.
And where's the one with the paper in it?
He's good.
Okay? Now, if you look at it, that one's getting really cloudy. So if we shine the light through that one, you can see the light beam in the water with no trouble at all, because there's little particles of paper in there. If we shine it through the other one, the pink one, oops, we see a little bit of a light beam going through there. See that, guys? You can see the light beam in the solution. And if we shine it through the gold one, you really aren't supposed to be able to see the light beam. And so we'll say you can't see the light beam in there because it's a genuine solution and not a suspension. If you guys at the other table would get those 3 vials, the G, one of the ends, and your water vial, get those together, and we will shine the light through and see what happens.
When is these?
Please, you're going to swap. Okay. There's your water. Okay.
Okay. Well,
With the suspension. Okay. You guys got your 3 here someplace? Okay. Excuse me. Which one is that? That's the gold solution. You really can see the light beam. That one's a little bit cloudier. You can see the scattering. And that one big time because a lot of particles of paper. Okay. Okay, so what we saw was we saw gold in a couple of different forms. In one case, it's what we call a salt, a gold salt, and it's in solution. That is the tube marked G. It's almost like dissolving sugar in water. It's totally dissolved, there's no solid particles left. On the other hand, the pink one is a suspension of gold nanoparticles. Now, one of the interesting things we talked about with gold nanoparticles was the fact that there are developing ways being developed, I guess I should say, for fighting cancer. And there are some really phenomenal things going on. In one case, chemists and research doctors are taking inert particles on the nano size, very, very tiny scale, coating them with gold, injecting them into people's bodies, and then shining a light on the body, and this actually ends up warming the tissues where the gold particles have associated, and it can kill tumors that way. The other way to use these gold nanoparticles in medical research is to test for something like meningitis. If a diseased protein for meningitis is tested against this red nanoparticle solution, the solution will turn blue. Now, we can't do that today because none of us hopefully is injected or has meningitis, but we can simulate that using a little bit of salt. I'm going to do it up here so that everybody can see it. We're going to take just a tiny bit of salt. That's probably way more than I need. And where's my lid?
Over there.
Ah, thank you.
It's a demo
Much more than I
from
know.
the,
If I take this and shake it, can you see the color change? Now, again, this has nothing to do with meningitis, but the addition of the salt has actually caused the original moderate-sized particles, the 6 to 15 or so nanometer particles, to agglomerate into bigger particles. These are about 90 nanometers apart, and they reflect, or you can see they are actually a blue color. So we have gold in 3 different colors: regular gold, nano gold, approximately 15 nanometers particles across, and other nano gold, approximately 90 nanometers across. So here we have an example of the same material with 3 different colors depending upon the size of the material, and you can see how the physical properties of the material have changed. Okay? Any questions on that, guys?
Bob, we need to clarify a
Yes.
little bit there.
Go ahead, Liz.
The nanoparticles are actually a colloid, not a suspension.
I beg your pardon.
They're colloids, they're not suspensions.
I beg your pardon. That is correct.
The paper is a suspension. Okay? Just
I beg your
as
pardon.
people
That is
watch the,
correct.
video.
Yeah.
so you shine the light through the, what you just did?
The bluish one.
Oh,
This one?
good question. I don't know. Haven't tried that one.
And can I ask, is the adding of the salt, is that a physical change? It says in
Yes.
the script that,
Yes.
so we really have just made them clump together?
Yes.
You can see the beam really clearly.
It causes an agglomeration. It destroys the citrate that was originally used to both reduce it and to coat the materials, coat the particles. The citrate coating has been destroyed, and that's why they agglomerate into bigger particles. Okay? So gold can be 3 different colors, at least. As a matter of fact, there's probably an entire spectrum of gold. If you Google nano gold, you'll find all kinds of information about that and how, in fact, you can have a whole spectrum of colors for gold. Okay? No questions about that, anybody? You guys over here, no questions about that? You're still adamantly shaking something. What do you got there?
The water.
The water. They're still trying to make those things dissolve. Maybe they will, maybe they won't. Okay, let's move on to something else, guys. Have you ever seen a lotus leaf? What's a lotus leaf? A lotus leaf is a lotus plant is a plant that grows in the tropics that wants to normally grow in muddy water, but the leaf itself is always nice and clean. How is that possible? What do you think?
It has waxy stuff on the outside that repels water.
Very, very good. That waxy stuff is, what do you think that is?
Nano something.
You got it. It's a nano material on the outside of that leaf. Yes,
It's called a cuticle.
it is. Okay, I didn't know that. Learn something every day. A cuticle. The only thing says it's called a cuticle. Okay, I'll buy that. Well, we're going to see if we can do something like that. Chemists have developed a new type of material called hydrobead. Anyone know what the word hydro is referring to? What does hydro refer to?
Water.
Water. So if we've got a material that is something called hydrobead, what do you suppose it might be doing if we use it? It might be causing water to bead, okay? Everybody has two little pieces of material in front of them. One piece of material has an X on it, and one piece of material doesn't. One of these pieces of material has been coated with a hydrobead material. The other one is a plain piece of material that hasn't been coated. What I'd like for you to do is you have two paper towels, these brown paper towels. Please unfold one of the paper towels and put the two pieces of fabric on the paper towel. Now you also have three what we call barrel pipettes in front of you. These little squeezy things that look like this. And over here at the middle of the table, I'm going to pass these down person by person. What I'd like for you to do is start with the cup marked K, and listen to me before you do it. I want you to take your pipette just like this. I want you to take your pipette and squeeze it, put it in the material, squeeze it, and suck some ketchup, that's ketchup obviously, suck some ketchup up until it's about maybe halfway up, but don't let go of the bulb, okay? Hold on to that bulb for dear life. Now, take your two pieces of material and at the top left-hand corner of each one of them, I'd like for you to put a little glob of ketchup. A little glob of ketchup right up in the corner. Maybe 1/4 of an inch wide or so. If you need some more ketchup, get a little bit more.
You just need to pass it down so everybody gets some.
Yes, it needs to be passed down.
That's so cool.
Okay, put a little ketchup, a little glob of ketchup, and pass it down. And then do the same thing and put your pipette on your paper towel when you're done, so you don't make a big mess.
On your paper towel. Wait,
That's someone else's paper towel.
Here, do you need more ketchup?
Just drop it on there. Drop it straight on. Make yourself a little glob. Then do the same thing with the chocolate syrup. Put a little glob right in the center of each of those at the top. Maybe like 1/4 of an inch glob. Okay? And then pass it down so that everybody else can get some. Then once everybody's got that, then we're going to take the third pipette and get some water and put a little bead of water about the same size in the other corner of the material. On the top of the piece of material.
What's the black bit?
Yeah, good luck getting it there, you know.
Chocolate
Come on, guys. The black stuff is chocolate syrup, Hershey's syrup, okay? What we're going to do is we're going to see if we can figure out which one of the pieces of fabric has been treated with this hydro bead material. Which one is going to act like the lotus leaf and shed the material? Now, don't do anything with it yet. Just let it sit there for a second until everybody finishes. So and when you're finished, you'll have a little glob of ketchup, a little glob of chocolate syrup, and a little glob of water on the material.
You can't keep the water on it.
That's the way it's supposed to be. You can't keep it on one, and you can't keep it running through the other one, probably. Now, your little pieces of material, one has an X on it, and one is plain. One doesn't have a little X. One of them is treated with the hydro bead material, and one of them isn't. Somebody's having fun. It's like the pennies last year with the water on it.
Oh, yeah.
Okay? Is everybody, okay, we still got some people finishing up here. So you need a little glob of ketchup, a little glob of chocolate syrup, and a little glob of water. A drop of water, whatever you want to call it. Each one about 1/4 of an inch across, something like that. Everybody all set?
No, we haven't got to the water yet.
Oh, you haven't got to the water yet.
Pass the water down. We're hogging the water.
Actually, you can use any of the water. You can use some of this water over here too. It's just a little bit you need.
Yeah, you can basically use any water.
Any old water is fine. Just regular old tap water.
Isn't that so cool?
It's not cool yet, because we haven't done anything yet. But it's gonna
Seriously, we haven't done
be.
anything?
Not yet. Well, not with that anyway.
Okay, that's enough.
Hey, what happened to your other bottle of water? Oh, there it is. Okay, it's still there.
Mine's just falling off.
Oh, really? I wonder why. Okay.
Now what?
Okay, everybody pretty much set now? Now, take the fabric without the X on it, pick it up by the corners, and pull the front edge towards you. Pick it up by the corners above the globs, and pull the front edge towards you so that the materials run down the material and onto the paper towel.
I need a little more ketchup.
Nah, you got enough ketchup. Not a hot dog.
My ketchup is not running.
Mine hasn't run.
Nothing
My chocolate
except for
syrup
the
is
water.
going very, very
The water ran.
slowly.
Well, the ketchup is a little bit viscous,
Put
a
water
little
in.
bit thick. That's right, you can take your pipette and spread the ketchup around a little bit if you want to.
Yeah, I'm gonna have to.
When we're all said and done, I'd like for you to do a couple of things. First of all, take your other paper towel, the other brown paper towel, and wipe each piece of material off. I'm sorry, before you do that, you got to take the other piece of material, the one with the X, and do the same thing. See if they'll run down that one. Do you notice any difference?
The ketchup just plopped off that.
Okay.
Mine too.
Same here.
What about the chocolate syrup?
It's not
Slowly
going anywhere.
trickling
Yeah, it's
down.
running off, but it looks a lot, it's not leaving a smudgy trail.
My ketchup still won't run.
Okay, now take the other paper towel and see if you can wipe off
Just take it.
the best you can both pieces of material.
Good, my ketchup came off.
Chocolate does leave a residue.
Now, do the best job you can in wiping each piece of material off. And by the way, demonstrators, this is a little bit different from what's in the script, okay? I think this way might be a little bit better than what's in the script. Wiping, this business of wiping the material off is not in the script. Okay, what do you see when you compare the fabric with the X on it and the fabric without the X? Which one is still stained after you wipe the material off? Aha!
The non-X.
The one without the X is stained? How about if you turn it up or turn it over and look at the back side? Has the material come, any of those materials seep through?
Yes.
Either one of them?
Both of them.
It's probably the one with the X on it that is the cleanest. that everything ran off of and that hasn't been stained through the material. So which one, if one of them doesn't stain very well, yeah, if one of them doesn't stain very much, and the material doesn't go through, or each of these liquids doesn't go through the fabric, which one do you think was treated with the Hydro-Bead coating material? The one with the X or the one without the X?
The one with the X.
Marks the spot.
Exactly.
They stuff on it.
Exactly. Like Bob said, X marks the spot. Yeah, it's the one with the X that was treated. And you guys have actually gone through a little scientific method there to prove which one was the treated one. And it worked, didn't it? Okay. You guys can do the same thing at home. You can take the treated piece of fabric home with you if you want. The other piece of fabric is kind of yucky because it has the material still kind of clinging to it. So you might want to leave that here. You got plenty of untreated piece of fabrics at home, old rags and God knows what. So if you want, you can take the X-rated piece of fabric home with you and leave the other one here. Okay? So far you're taking the wire, the memory wire, you can take the paper clip if you like, and now you're going to take the little piece of fabric with the X on it home with you, and you can repeat some of these things at home. Okay, one more thing to do. One more thing. How many people have been to the beach?
I went to the beach.
Have you been to the beach?
I went to the beach on Independence Day this year.
You did, huh? Okay. Well, beaches obviously have a lot of sand on them, don't they? And have you ever walked through the sand and maybe got it squishy between your toes and all that? That is kind of characteristic of sand. When you have sand in water, what does sand do in water? It kind of mixes with it, doesn't it? It kind of forms almost like its own little liquid.
It kind of forms like sludge.
Yeah, like a sludge or a sludgy,
Like
sloppy mess kind of.
Like
Okay.
sludgy mud stuff.
Yeah, you can just see it between your toes, right, when you're walking on the beach. Well, chemists have come up with a treatment that can be put on sand that's only a nano layer thick. Basically 1 atomic layer thick. And what it does is it has changed the properties of sand altogether. Each of you guys has a tube with some colored material in it in front of you.
That's marked NS.
It's got NS on it, correct. NS for nano sand. Now, if you'll watch what I'm going to do with the nano sand, and then you guys can do it yourself. First of all, I'm going to take and I'm going to put about a half a teaspoonful of this nano sand in the teaspoon. Okay? Just about half full. Now, I'm going to take the cup of water marked W in front of you, and I'm going to sprinkle some of this sand on the surface. Now watch what I do. I'm going to sprinkle just a little bit on the surface, just to cover the surface. And what do you see? What do you see? The little bit of sand on the surface is actually floating on the surface, isn't it?
What happens if you let them the whole thing?
Now what happens, good question. What happens if you take the whole thing and just dump it into the water?
Whoa.
What do you see?
That's cool.
What's it look like? It looks like it has kind of a shiny, looks like a shiny coating around it, doesn't it?
And if you
That's
lift it up,
interesting.
it doesn't.
Then if you touch it when it's underwater, it's not even wet.
That's right, it's not even wet, that's correct.
It's not even wet.
Now, you can take your spoon and you can grab a little bit of a sample of it and put it back in your spoon and dump the water off of your spoon, and guess what? The sand is still dry.
Don't
We
you-
call this nano sand, or some people call it magic sand. You see that kind of a silvery luster around it? The kind of silvery luster around it? What that is that's an air bubble trapped right along the surface. Now, you've all got another cup marked D. Another cup marked D. If you take your first cup with the magic sand in it and pour it gently, pour the water into the other cup.
Can we use HW instead?
Yeah, sure.
You could. Pour it gently and leave most of the sand in the cup behind. What have you got? What does the sand look like when you're done with it? It's dry. And you know what? If you take the sand and you put it on a paper towel, we're not going to do that right now, but if you take it and you put it on a paper towel, you can actually dry it off and it'll look like the same sand that you started with because the water simply won't stick to it. And you can play this game all you want. You can pour the water back in and get the same kind of magic sand, or you can pour the water back off and the sand is dry again. Okay? Now you guys are going to be able to take the magic sand home with you. What I'd like for you to do is take one of these white paper towels up in front of you. If I can get them apart. There we go. Take one of the white paper towels, and after you pour the water off, or almost all the water that you can get,
You can't do it. Just keep
just do it very, very gently and very slowly, and it should work okay.
So what happens?
Hang on just a minute.
Pour the water.
You can use the spoon.
Wait, take your spoon.
Yeah, you might use a spoon a little bit.
Dunk all your magic sand under water as much as you can. Yeah, it is, a lot of it is. but-
Yeah, some of it will float, but most of it will go under the water. Pour the water off nice and slowly and gently.
Like that?
And then when you've got most of the water poured
We're
off,
gonna pour it in here, but.
pour the magic sand onto the paper towel and try to dry it off.
What do you do with the one that? What do you
That's
do
just
with?
good.
Well, hang on just a minute. Now comes the hard part. I'd like for you to use a buddy system. Don't try to do this by yourself. But what I'd like for you to do is one person take the vial, 50 ml vial that the sand came out of, and the other person, and hold that, and the other person try to pour the sand very gently, very carefully back in. And then you can take your magic sand home with you. Okay? And it's almost the same as when you started. Now, one last thing. Yeah, try to scrape up the magic sand if you spilled any and take it home with you. Because it's all fun stuff. Last thing we have is you have a spoon at your place, and there's a vial of regular sand at the table. This is just sand that we purchased at Lowe's, I believe it was, play sand. Take the top off of that vial and pass that down, and very carefully pour maybe a teaspoonful of that sand out. Or or you can just take it and pour it right into your cup that still has the water in it. Okay? And see if that sand acts like magic sand or regular sand. Yep, it's regular old play sand from Lowe's. Easy does it, guys.
Oh.
Oh, there you go. Okay. Now, take that and put it in the water, and does it do the same thing that magic sand did?
No.
You can stir it around a little bit. Yeah, it just goes plop, and that's it. It doesn't do anything. You know why? Why do you think that is? Because it's regular sand, not nano sand. The nano sand has a layer of a material we call silicone. It's a special chemical the chemists have come up with. There's a silicone layer on it that was put up by vapor deposition, by the way. And it was, because of that layer of silicone, what would you say the sand is? If we use terms like hydrophobic or hydrophilic, hydrophilic means it loves water, hydrophobic means it hates water. What do you think the magic sand is? Is it hydrophobic? Does it hate the water? Or is it hydrophilic? Does it love the water? It's hydrophobic. It hates the water, right? What's the regular sand? The regular sand is hydrophilic. You know what's interesting though? If you went into your garage at home and got some of Dad's motor oil and poured the motor oil onto the magic sand, what do you suppose would happen then?
The same thing as the normal sand.
Same thing as the normal sand in water. So the nano sand in oil would behave the same as the regular sand in water. Is that what you're saying? You're right. That's exactly what would happen. Now don't try that until you ask Dad, okay? And you might also not want to use, if you did try to do that at some point, you might not want to use all of your nano sand because you might not be able to get it separated again. Okay? Any questions on anything we talked about today, guys? Yes?
Is there any extra nano sand?
You'll get it.
Well, I'll tell you what. Your mom might be able to come up with a little bit because she has several of our kids and she probably won't use it all, okay? But the answer is yes, we have some more. And when National Chemistry Week is all over, ask your mom to give me a call or send me an email. Maybe we can get you some more. Okay? Okay. Well, that's pretty much it for our National Chemistry Week fun and games for this year. Demonstrators, the only things we want returned are the vials with the ferrofluid. It's all in the script. Hopefully everybody's got a copy of the script. The ferrofluid vials and the gold
Can we take these out?
nanoparticle vials. Yeah, you can take the one with the paper in it. The gold nanoparticles and the regular gold salt, we'd like those back. The magnets and the ferrofluid. You guys, you students can take the memory wire home with you, and you can take the paper clip, and you can take your magic sand, and you can have the vial that the magic sand came in.
But you want not just the vials, but the solutions with the gold particles?
Yes, please. They all have nanofilm. They all have parafilm on them, and if you just kind of leave them intact, and like we told the students here, don't fool with anything until you're told to. And they're never told to take the parafilm off, so they shouldn't be undone, if you would. Yes, return all of that. The specific instructions are in the script. And one last thing, there is on the website, if you go to the volunteers tab and click on that, there is a survey form. We've tried paper, hard copy survey forms in the past. Sometimes we get them back, sometimes we don't get them back, sometimes they're tucked in here or there or wherever. Hopefully with the electronic surveys, if you guys will go and fill out those surveys, we really appreciate that. We need the feedback for some of the things we like to do with the data. Okay? Alrighty, thank you very much for coming, and hopefully you'll have a good time with your own demonstration.
Thank you.
And I hope you guys have a good time.
What was your favorite experiment?
Oh yeah, what was your favorite experiment?
Which one was good?
I like the memory wire.
You like the memory
And
wire?
the nano
My
sand.
favorite was nano sand.
The nano sand, huh?
Can you choose two favorites?
Just
Can you choose two favorites? Hang on just a minute, Bob. Yeah, sure. What's your other favorite?